Number systems. In this presentation, we'll see some of different types of number systems used in digital field. Number systems other than the familiar decimal number system are used in computer field and digital systems. Digital computers internally use the binary number system to represent data and perform arithmetic calculations. Other than decimal number system, we are using binary number system, octal number system and hexadecimal number system. In this presentation, the objectives of this presentation are to understand the decimal, binary, octal and hexadecimal number systems and conversion between different number systems, and then to understand BCD codes and alphanumeric codes used in digital systems. The first one is the introduction. Number system relates quantities and symbols. The base or radix of a number system represents the number of digits or basic symbols in that particular number system. For example, in decimal system, the base is 10 because we are using 10 symbols or numbers in decimal system. In the same way, in the binary number system, the base is 2 because here we are using only 2 symbols, either 0 or 1. And each digit in the binary number has a value, or it is also known as weight, and that is given in the table here. The LSB of a binary digit has the weight of 1, that is 2 power 0 is equal to 1. And next to is the second digit, 2 power 1 has a weight value of 2. Like that it goes on. Here is an example which represents the conversion between binary to decimal. A binary number can be converted into decimal by multiplying each of the binary bit by its weight value or the place value. Here the LSB is multiplied by its weighted value 1, and then 2, 4 and 8, like that. After that, the values are added to get the final number. So the binary number 1001 is equivalent to the decimal number 9. So this is how to convert the binary number into decimal. Next, to convert a decimal into binary. To convert a decimal number into binary, we have to divide the number by 2, and for every division operation, the remainder is taken into account, and finally all the remainders are written in the reverse order. So here is an example. This example shows how to convert a decimal number into binary. So the binary equivalent of 12 is equal to 1100. So it is divided by 2, and every time the remainder is written on the right side, and finally the remainder is taken in the reverse order 1, 1, 0 and 0. And next one is octal number system. Octal number system has a base of 8 because it uses 8 symbols from 0 to 7. In the octal number system, each digit corresponds to the power of 8, that is its weight value is calculated 8 power 0, 8 power 1, 8 power 3, like that, depending upon the digit's place value. Here, how to convert the octal number into decimal or decimal to octal. So as we have seen in the binary number system, to convert an octal number into decimal, the octal digit is multiplied by its weight, that is each digit is multiplied by 8 power, first LSB is multiplied by 8 power 0, and then 8 power 1, and next one is 8 power 2, like that. Finally all the answers are added to get the result. And next one is decimal to octal conversion. Here the number is divided by 8 progressively, and every time the remainder is taken into account, and finally all the remainders are written in the reverse order. So that will give the octal equivalent of a decimal number. An octal to binary conversion. Each octal digit is represented by 3 binary bits, because the maximum value of octal digit is 7, and that can be represented in binary using 3 bits, 1 1 1, which is equal to 7. So in octal system, it is each digit is represented in binary using 3 bits. To convert a given octal number into binary, just we are writing the equivalent binary code of each octal number. Here it is 7. The equivalent octal binary code is 111, and here it is 5, and its binary equivalent is 101. Like that, every digit is converted into its binary form. And to convert the binary into octal, the number of bits are grouped into 3 from LSB. Here this is a LSB. Here it is grouped into 3 1 0 1, and the decimal or octal equivalent is 5. In this way, all the binary bits are grouped into 3, and their octal equivalent is written here. This is the method to convert the binary bit to octal. Another number system is called hexadecimal number system. Its base value is 16 because it has 16 different symbols, 0 to 9, and then alphabet A to F. And this table shows the decimal number, hexadecimal number, and its binary equivalent. So the decimal number starts from 0 to 15, and for these 16 numbers we have a hexadecimal character starting from 0 to 9, and then from A to F. And the binary equivalent of the hexadecimal is represented by 4 binary bits, because the maximum number of hexadecimal is F, which is equivalent to 15 in decimal, and it can be represented by the binary using 4 bits, and its value is 1111. So any hexadecimal number can be represented in binary using 4 bits. And next one is how to convert binary to hexadecimal. The given binary number is grouped into 4 from the LSB. So this is the first 4 bits, and its equivalent number is E here, and the next 4 bits are grouped and its equivalent is 2. Like that, any binary number can be converted into hexadecimal form by grouping them into 4 bits. Next, hexadecimal to binary. As we have seen in the octal system, each hexadecimal digit is converted into its binary equivalent using 4 bits. So this is an example. And to convert the decimal to hexadecimal and hexadecimal to decimal, the procedure is same as that of we have seen in the octal number system. To convert a decimal to hexadecimal, the given decimal number is divided by 16 progressively, and every time the remainder is taken. Finally, the number is divided by 16, and each division and then written in the reverse order. So the number will be a hexadecimal number. And to convert hexadecimal to decimal, each digit of the hexadecimal number is multiplied by its weight value, which is calculated by the power of 16. Next, we will see about decimal codes or binary codes. The binary code system is used in any computer or any digital electronic systems to represent a number or any other character. Binary coded, the important codes are, the number of codes are used in computers, and important codes are ASCII code and EBCD code. They are known as alphanumeric codes, and binary coded decimal is a code which represents each decimal number into binary form. That is, each decimal digit from 0 to 9 is represented in binary using 4 bits, and that is given here. 0 is represented by 0 0 0 0, and 1 is represented by 1 0 0 0. Like that, up to 9 we are representing each decimal digit using 4 group of bits. So this is known as binary code. And next one is alphanumeric code. In computers and printers or any other digital devices, we are using alphanumeric codes to process any alphabet or numeric characters, numeric informations. The characters to be coded are alphabets, numerals, and special characters. In order to code a character, string of binary digits are used. There are two standard codes. They are known as alphanumeric codes used in computers and printers. They are ASCII code and EBCD code. ASCII code is American Standard Code for Information Interchange, and EBCD is Extended Binary Coded Decimal Interchange Code. ASCII is a 7-bit code. In most of the keyboards we are using ASCII code to represent each alphanumerical characters, and EBCD code is a 8-bit code, fixed length code. It is more widely used in printers. So these are some examples of alphanumeric codes. Next we are going to see Boolean algebra. An English mathematician, George Boole, developed rules for manipulations of binary variables known as Boolean algebra. This is the basis for all digital systems like computers, calculators, etc. Binary variables can be represented by a letter, symbol such as A, B, X, Y, etc. The variable can have only one of the two possible values at any time, either 0 or 1. So the operators used in Boolean algebra are plus symbol, equal to symbol, dot symbol, and bar. Plus symbol is known as OR, logical OR. Dot symbol is known as logical AND, and bar symbol is known as logical NOT. And here the basic laws of Boolean algebra are given here. You can go through this. And here the plus symbols or OR symbols are known as OR law of Boolean algebra, and the dot represents the OR laws of Boolean algebra. And De Morgan's theorem. So this is used to simplify any Boolean expression. The De Morgan's theorem gives two statements, that is a plus b whole bar equal to a bar dot b bar, and a dot b whole bar is equal to a bar plus b bar. So using any Boolean algebra and De Morgan's theorem, we can simplify any of the logical expressions. De Morgan's theorems also used to convert any logical expression in sum of product form or product of sums form, and also the De Morgan's theorems are used to simplify Boolean expressions easily. Next we are going to see about the logic gates. A gate is a logic circuit with one output and one or more inputs. The output signal occurs only for certain input combinations. The input and output signals are digital in nature, that is 0 or 1 or low or high. All the possible input combinations and their corresponding output conditions are noted in a table known as truth table. In a digital system, two different voltage levels are used to represent the logic level 0 and 1. If a high voltage is used, then it represents logic 1, and a low voltage level represents logical 0. Now we are going to see different types of gates. AND gate. In this gate, the output is high only when two inputs are high. When any one of the input is low, the output will be 0. And the Boolean expression for AND gate is y is equal to a dot b. And next is OR gate. Here, when any one of the input is high, the output goes high, and its Boolean expression is y is equal to a plus b. NOT gate. It is also known as inverter because it inverts the given input. If a is given, the output will be a bar. That is, the complement of the input is received at the output. Its Boolean expression is y is equal to a bar. And two gates are known as universal gates. They are NAND gate and NOR gate, because any kind of logic circuit can be designed using only these two gates. So they are known as universal logic gates. A NAND gate is nothing but the combination of AND gate and an inverter, and it is the reverse of AND gate. When all the inputs are high, its output goes low. And NOR gate is a combination of OR gate and inverter, and its output is high only when all the inputs are 0. Next one is XOR gate. It is also known as exclusive OR gate, and it gives an output for alternate inputs. That is, for 0 and 1 combination, it gives output. When both the inputs are same, the output will become 0. So these are some basic gates, logic gates used in logical circuits. And Boolean expression which gives any logical circuit. And here is an example, and the truth table capture the output of a Boolean expression. A column for each input plus the output, a row for each combination of input values. So we have seen some of the number systems used in digital systems and the basic building block of a logic circuit, which are known as gates. And to simplify a Boolean expression or logical expression, we are using Boolean algebra and De Morgan's theorem. So we have seen all these things. Thank you.